Question 3. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. The oil slick takes the form of a right circular cylinder with both its radius and height changing with time. Note the volume V of a right circular cylinder with radius r and height h is given by V equals pi r squared h. Alrighty, part A. At the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeters, the radius is increasing at the rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time in centimeters per minute? Just one comment on this question, even though we usually will only have 2 calculator problems, since this is an older problem, we do get to use our calculator on it. I'm going to just write down some information. They told me that r is equal to 100. They told me that h is equal to 0.5. They told me that the radius is increasing, so they told me that dr dt is equal to 2.5, and they're asking me for the rate of change of the height of the oil slick. So they're asking me for dh dt, and that is what I know. And I think that is pretty much all they've given me in the problem. Okay, so from here, we are going to see if we can figure this out. We are going to have volume equals pi r squared h. I'm going to be attempting to take the derivative of this. So we are going to do that. To take the derivative of the left side, it will just be dv dt. And then to take the derivative of the right side, we will have to use the product rule since we're dealing with 2 separate variables. F prime, the derivative of pi r squared is 2 pi r dr dt. And g prime, the derivative of h will just be 1 dh dt. All right, so using the product rule, I'm going to get dv dt equals f prime times g. So I'm going to get 2 pi r dr dt times h plus f g prime pi r squared dh dt. All right, now I'm just going to try to see if I can plug in stuff. Remember, we're looking for dh dt. They definitely told me r and they told me h, which will help. I do notice that I don't see a dv dt, but if you can remember, dv dt is how fast the volume is changing, and they did say the volume is increasing at a rate of 2,000 cubic centimeters per minute. So we actually know that dv dt is equal to 2,000, and it's increasing, so it's positive. So now we have 2,000 equals 2 pi, the radius is 100, dr dt is 2.5, so 2.5, you can read that, times the height is 0.5, and then plus pi, the radius again is 100 squared times dh dt. And please remember, we're going to be solving for dh dt. All right, when I do that, let's see, I'm going to get 2,000 equals, oh boy, I don't have my calculator handy. I do know that if I solve this problem, I will end up getting an answer of dh dt is going to equal 0.038 or 0.039 they will accept, and that we're talking about the height changing. So this will be centimeters per minute. If you'd like to see this worked out, hopefully. You don't need to. I guess I'll do it without using a calculator. I know that I need to move this over to the other side, so this will be 2,000 minus whatever this answer turns out to be. It'll be 2 pi times 100 times 2.5 times 0.5, and then it will equal pi times 100 squared dh dt. And then to solve for that, whatever this answer is, we'll divide it by pi times 100 squared, and that should give you the 0.038 or the 0.039. All right, so points on this part was worth, 4 points. If you wrote somewhere on your paper that dv dt was equal to 2,000, you got a point. If you, well, actually you had to write that, and you had to write dr dt equals 2.5. So if you wrote both of those on your paper, give yourself a point. If you found a derivative, so if you have this expression right here, that is actually worth 2 points. So if you made a mistake somewhere in there, but you took the derivative, you might earn yourself 1 point, and then you're going to get 1 point for getting this final answer. All right, part B. A recovery device arrives on the scene, woohoo! And the rate at which oil is removed is r of t equals 400 squared of t cubic centimeters per minute, where t is the time in minutes since the device began working. Oil continues to leak at the rate of 2,000 cubic centimeters per minute. Find the time t when the oil slick reaches its maximum volume. So we are looking for a maximum volume. To get a maximum volume, we're going to take the derivative of the volume, which would be how fast the volume is changing, and we'll set it equal to 0. So we know that oil is, so we basically are going to be finding dV dt. How fast is the volume of this oil changing? To get that, we know that we have oil that's leaking out, and then we have oil being removed. So we have 2,000 because that's the rate that it's leaking, and then we're going to do minus the oil that we're removing. So minus 400 square root t, and then we will set that equal to 0. Sorry about that. Okay, we do get to use our calculator on this. So if you set this equal to 0, you can use your calculator, and you can use the 0 feature of your calculator, and you should get t equals 25. Another way, if you didn't want to do that, we could do 2,000 equals 400 squared to t. We could divide both sides by 400. We'd get 5 equals the square root of t, so to get rid of the square root, we'll take the square of both sides and we get t equals 25. So in either case, we get t equals 25. So we found the time to show that it's a maximum. We actually are going to do a v prime chart. And if we put 25 in there, if we put in, let's say I put in 0 even, I'm going to get a positive value. If I put 50 in or something like that, I will get a negative value. So for sure that it reaches a maximum, and I should not just draw my chart, I should say the volume reaches a maximum at t equals 25, and that will be because v prime dv dt, or v prime, changes from positive to negative. All right, that problem will be worth 3 points. If somewhere you have this, you've taken 2,000 minus r of t and you've set it equal to 0, you're going to get a point for that. And then if you came up with the answer of 25, you're going to give yourself a point. And then if you're able to justify your answer, you're going to get your 3rd point. Okay, part C, by the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Write, but do not evaluate, an expression and involving an integral that gives the volume of the oil at the time found in part B. So we found, so basically from 0 minutes until 25 minutes, we were having some issues with the problem. So we're going to go 0 to 25, and again, it's going to be that 2,000 minus 400 square root of t, because it's the oil that was leaking out minus the oil that we're removing. And then we're going to take this, and then we're going to add. So this will give us how much oil happened over that 25 minutes, but we started with 60,000. So I do need to add 60,000 to my initial answer, and then that will be my setup. And then from here, we're pretty much done with this problem. I'm going to get 2 points. First of all, if I have my limits 0 to 25 and I included the plus 60,000, I'm going to get a point. And then if I have the proper 2,000, if I have the proper 2,000 minus 400 square root of t, I'm going to get my 2nd point. So hopefully we got some points on that one.